Welcome to the lecture 10 of remainders. In this lecture, we will discuss some problems on digits and numbers. Before we start our lecture, I invite you to join to our Telegram CAT group. I will put this link in the description. You can join there. Okay, so the first question is, the number n equal to 1, 2, 3, 4, 5, 6 and so on till 55 is formed by writing numbers from 1 to 55 side by side. Okay, so let's say I write all these numbers side by side 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on till 54, 55. Okay. Find the remainder when this number n is divided by 16. So I have to find the remainder. Now here you will have to know a theorem, or not a theorem per se, a property of 2 raised power n, right? You must have heard that 2 raised power n. Let's say if I want to find what is the remainder when I divide any number by 2. So this number, howsoever big it is, you will simply take the unit digit and you will divide by 2 and you will get your correct answer, right? You will get your correct remainder. Okay. Similarly, if you want to find the remainder when you divide by 4, and what is 4? 4 is nothing but 2 square, right? So n by 2 square. So we will take last 2 digits, right? So actually for any power of 2, let's say 2 raised power k, you will simply take last k digits. You will simply take last k digits and you will divide by 2 raised power k and you will get your correct remainder. So 16 is nothing but 2 raised power 4. So I will take last 4 digits of this number and I will divide by 16, and whatever my answer is, that is the correct remainder. It means that our question reduces to 54, 55 by 16. Whatever the remainder is there, this is the correct answer. So you can divide 16 into 3, 48, 6, 65, 16 into 4, 64. That would be 1, and that is the correct answer is 15, I think, right? So 15 is the correct remainder. So if you don't know this property, you can see how hard this question will become for you, right? So you must know that any power of 2, there is a property. If we want to find the remainder for any power, let's say 2 raised power 7. So you will simply take last 7 digits and you will divide by that by 128 and you will get your correct answer, right? So let's move on to the next question. We have the 5-digit number 2018U is divisible by 9. What is the remainder when divided by 8? Okay, now this is easy question. You know that the property of divisibility by 9 is that you sum all the digits and it has to be divisible by 9. So 2 plus 0 plus 1 plus 8 plus u, it has to be divisible by 9. So from here you will get 2 plus 1, 3, 8, 11 plus u, 11 plus u divided by 9. Now if it is divisible by 9, so can I say that remainder is 0, right? In other words, you can say that. Now what will be the value of u? Now remember, u is a digit, right? U is a digit. It is not a number. So u will be ranging from 0 to 9. 0 to 9. So if you put 0, so no. So you can put this value u as 7, right? For that only it will be divisible by 9. 9 into 2, 18. So 11 plus 7, 18. So the value of u is 7. Now you can get your number 20187. Now you can divide this by 8. Now again same property. Do I need to divide the whole number? No. This is 2 raised power 3, right? So I can simply take last 3 digits and I can divide by 8. So 187 by 8. What is the remainder? 8 into 2, 16. 227. 8 into 3, 24. So remainder is 3. Right? So finally our correct answer is 3. I hope this is clear to you. 3 is the correct answer. Okay, let's move on to the next question. N is a 2-digit number. When n is divided by 9, the remainder is 1. When n is divided by 10, the remainder is 3. What is the remainder when n is divided by 11? Okay, now this second line, this line is very important. Whenever I take a number n, I divide by 10 and I get remainder. Actually, this remainder is nothing but the unit digit. This gives us the unit digit. So if this remainder is 3, it means that out of 2 digits, let's say 2-digit number is there, it is 2-digit number, right? And so this unit digit is 3. This is directly given in the question in other format, right? I hope you are aware of this particular property, that if you want to find the unit digit of any number, you simply divide by 10 and get the remainder, right? Now I simply need this second digit, and for that I can use the first line, right? N is divided by 9, the remainder is 1. So what will be the value of here in order to get remainder of 1 when I divide by 9? So that will be of the format 9k plus 1, right? So this will be either 10 or 19. If I put k equal to 1, so this will give me 10. If I put k equal to 2, so this will give me 19. So in order to get 19, this has to be 16. Obviously this has to be a digit, right? So in order to get 10, I will put 7, right? So it means that my 2-digit number is 73. Now what is the remainder when n is divided by 11? So n is equal to 73. If I divide by 11, so what will be the remainder? 11 into 6, 66. So 7. 7 is the remainder. Okay. So finally the correct answer is 7. The correct answer is 7. So this was an easy question. How many positive 3-digit integers have a remainder of 2 when divided by 6, 5 when divided by 9, and the remainder of 7 when divided by 11? Actually, this is a good question. So let's say there is a number n, and when I divide by 2, I get a when I divide by 6, I get remainder of 2, right? So can I say that this will be 6k plus 2 type, right? Now same number, when I divide by 9, let's say k dash, I get remainder of 5. Same number when I divide by 11, let's say k double dash plus 7. Now all these remainders are different, but one thing is common there. If you notice, there is a clever pattern here. Actually, all these have same negative remainders, right? Negative remainder is 4. Here also negative remainder is 4. Here also negative remainder is 4. So can I rewrite all of them in terms of same remainder, right? If I can write all these numbers, all these forms in the same remainder, then we can easily solve that, right? So can I say that let us call this factor, these multiplying factors as 6a minus 4, 9b minus 4, 11c minus 4, right? So 6a minus 4, 9b minus 4, 11c minus 4. Now since we have same remainders, can I say that this will be of the format of LCM of 6, 9, 11 into some multiplier k minus 4, right? So 6, 9, 11, what will be the remainder? So the remainder would, not remainder, what will be the LCM? LCM will be, so from 6 and 9, my LCM would be 18, and 18 doesn't have anything common from 11. So 11 into 18, that will be 180 plus 18, 198. Okay. So my number is of the format of 198k minus 4. Now I will keep on changing this value. I will keep on changing this value of k, and I will get new numbers. So k equal to 1 will give me 198 into 1 minus 4, that will be 194. Actually, we have to find how many, right? We don't actually concerned with this number. So simply let us try to find how many numbers. K equal to 2 will also give me a number, and so on. And I have to find 3-digit integers only. So how can I stop? From where I will have to stop? Let's say k equal to 6. So this will be approximately, let's say this is 200 into 6. So 1200 minus 4, that will be 208, right? And slightly lesser than that. So obviously k equal to 6 will give me an integer which will be greater than 3-digit integer, right? So from k equal to 1 to k equal to 5, I cannot go beyond that 5. So k equal to 1 to 5, it means that only 5 such integers are there, right? It means that only 5 such integers are there. So how many positive 3-digit integers are there? 5 such integers. 5 such 3-digit integers. I hope this is clear to you, right? So this was a good question actually. If you have to notice this pattern, that even though these remainders are different, but they are same in negative remainders. And once you find that these are same negative remainders, you can convert them to an easy format, right? Otherwise, it will be very difficult to solve for you. I hope this is clear to you. Okay, now we move on to an interesting concept of digital sum. Now, what is digital sum? So digital sum is nothing but single digit value obtained by adding the digits of any number iteratively. For example, if you don't understand this definition, what I will do? So let's say I take this current year 2023. Now if I ask you what is the digital sum of this, so you will add all the digits 3 to 5, 0, 5 to 7, so 7. But let's say I choose 9, 8, 7, 6, 5. So you will add all the digits, 9, 8, 17, 7, 24, 30, 35. Now you can't say that 35, you will have to add them again. You will keep on adding the digits of number until and unless you get single digit value, right? You can't stop before that. So 3 plus 5, 8. So the digital sum of this number is 8. I hope you are aware of this, right? I hope you understood this concept, that you will keep on adding the digits until and unless you get a single digit value. You cannot stop before that. Okay, so let us discuss a few more examples. So let's say I have, let me take an example of 4, 5. Okay, so the digital sum would be 9. Now what I will do is I will keep on adding 9. So if I add 9, so I will get 54. Again the digital sum is 9. If I again add 9, so I will get 63. Again digital sum is 9, right? So digital sum is not changing, if you notice. Now let's say I take a number 13. The digital sum is 4. If I add 9, I will get 22. Again digital sum is 4. If I add 9, 31. Again digital sum is 4. If I add 9, again 40. Again digital sum. So digital sum and 9, these are very actually peculiar things. These form a pattern. So it says that there is a property that digital sum will not change. Digital sum will not change by adding or subtracting. 9. So if you keep on adding or subtracting 9, your digital sum is not going to change, right? So in other words, what we can say is that if we have an AP, with common difference of 9, it means that all the terms of that AP, all the terms of that AP arithmetic progression will have same digital sum, right? They will have same digital sum, right? I will show you an example. So let's say I take 77, and if I have to make a common difference of 9, so let's say 86, 95, 105. So this is an AP with common difference of 9. Now find the digital sum. 7 plus 7, 14, so 5. 8, 7, 14, 5. 9, 5, 14, 5. 1 plus 0 plus 4, 5. So all of these have same digital sum of 5, right? So this is a very important property of any AP with common difference of 9, that they all will have same digital sum, right? So this is an important property you can remember. Now one more property is there, that if you want to find digital sum of any number, right? Actually it is using the last property only, that if we add or subtract 9, this digital sum is not going to change. In other words, how we can use this property is that if we want to find digital sum of any number, we can find this another way as well. What we can do is we can take that number, we can divide that by 9, and we can simply find the remainder. So this is always going to give me a digital sum of that number. And this particular property is useful in the larger power values. We will solve some questions. So for example, let me take a number. For example, let's say 7. No, sorry, let me take like this. Let's say 8 raised power 2025. And I have to find the digital sum of this number, right? Now, obviously, I can't find digital sum like this way, right? This will be very difficult. How can I define 2025 power? But this property says that if I take the remainder by dividing 9, we can get the digital sum. So our program reduces to divide by 9 and find the remainder. Now 8 will give me a negative remainder of -1. So -1 raised power 2025 by 9 remainder. Now -1 raised power odd power. This is always going to give me -1 by 9 remainder, and this will give me 9 minus 1 8. So our digital sum is 8, right? So the digital sum of this number is 8. So this way we can leverage this particular property very efficiently. Now let us discuss a few problems. So what is the digital sum of 2025 factorial? Now obviously I can't find all, I can't write all these numbers, right? 2025 into 2024 and so on. That will be very stupid thing to do. So what we can simply do is 2025 factorial by 9. What is the remainder? That is equivalent to digital sum, right? Now tell me one thing. 2025 factorial will obviously always contain 9, right? If you write this as like 2025, 2024 and so on, obviously you will get 9 at some place, right? 9 into 8 into 7 and 1. So it means that if I divide this big number by 9, so obviously my remainder is going to be 0 because it is divisible by 9. Now since my remainder is going to be 0, can I say that digital sum is 0? No. See, any number other than 0 can't have digital sum as 0, right? For example, let's say 1. So digital sum is 1. 2, let's say 1 0, so digital sum is 1. 1 9, so again 1. So whenever we get digital sum as 0 and this number is obviously non-zero, so we can say that digital sum is nothing but 0 plus 9 9. Okay, so whenever you get digital sum as 0 of a non-zero number, you can say that your digital sum is nothing but 9. Okay, I hope you got the point. Okay, what is the digital sum of 28 raised power 2025? Now again same way, 28 raised power 2025 by 9. What is the remainder? Now this question is equivalent to this one, right? Now 28 by 9, remainder is 1, right? 9 into 3 27, so remainder is 1. 1 raised power 2025 by 9 remainder, and this is nothing but remainder 1. So it means that this is the digital sum also. This is the digital sum. So correct answer is 1. So you can see, you can appreciate now how this property is important, right? Otherwise, how will you find the digital sum of this big number, right? It will be very difficult for you to find digital sum of these large numbers, right? For example, this 8 raised power 2025, 2025 factorial, 28 raised power 2025. So all such numbers are very huge. And in order to find digital sum, you have to know a very important property, and this property helps you in that, right? Okay, I hope you understood all such questions and all these concepts of digital sum and all those. So I have a practice question for you, and you have to answer it in the comment section. The question says, what is the digital sum of 899 raised power 2048? So this is also a good question, and you can again use the very same property of 9, right? Okay, so this lecture is done, and I again invite you to join our Telegram cat group. You can join this group using the link in the description. I will put this link in the description also. Now, if you want to join for other MBA exams like CET, TISNET, CMAT, then also I will put these links in the description, right? Okay, so thank you. If you like our content, then please support our channel by subscribing, and you can recommend it to your other friends and colleagues who are preparing for CAT and other MBA exams, right? So thank you.